Hey, we're going to be talking about how high blood pressure affects the biomechanics of the aortic valve.
Hypertension is a major health issue in many countries in the world. In the US, it affects about 25% of people roughly, and in some countries like Poland, the prevalence goes up all the way to 70%. The aortic valve is the valve in the heart that separates the left ventricle from the aorta, and because the left ventricle is the area with the highest pressures, we would hypothesize that the aortic valve would have the highest stresses in the heart. About 95,000 procedures are done on the aortic valve because of this, and many studies have shown that there is a correlation between hypertension and aortic valve disease occurrence. Some other techniques used to model the biomechanics of the heart are dual photogrammetry, where black dots are placed on the aortic valve and the strain is measured by their movement, and transcriptional techniques using RNA expression.
We wanted to create a mathematical model of the heart valve in order to compare the stresses and strains within the heart valve between hypertension and normal blood pressure. However, the heart valve is not easy to model. Not only is it a non-uniform shape, it is also composed of several layers of different materials, as shown in the leftmost figure. We made several assumptions to simplify our model. We assumed the heart valve to be a flat, even thickness cylinder with uniform material and uniform load divided into three equal leaflets. We were able to treat the leaflet as a bending problem in cylindrical coordinates and received this equation for the max radial stress as seen in the bottom right. We were then able to use values for blood pressure, area of the heart valve, and the thickness of the heart valve found from literature in order to find our final value for predicted radial stress.
So after using the equations from the last slide to calculate stresses at normal blood pressure, 120 millimeters of mercury of pressure, and we found that it was 3.7 millipascals of radial stress, and then at 160 millimeters mercury pressure hypertension, we found that it's 4.93 megapascals stress. We're using our calculated literature values. We also found that it was 1.62 kilopascals and 1.82 kilopascals. So even though these are off by about 3 orders of magnitude, the stress still did increase in both cases. The actual experimental values found from the literature were in the range of 200 to 400 kilopascals, however.
And these differences in values can be attributed to the oversimplification of our model. We assumed our shape to be a flat disk with uniform thickness, but in reality is more of a bulging disk with varying thicknesses. In our model, we also simplified it to a simple bending problem, such as one we've done in class, but that is much too simple of a movement. Lastly, we assume that each leaflet acts independently, but in reality they touch each other and interact as one. Based on our results, our model does work to some degree, as we see that an increase in blood pressure leads to an increase in strain of the aortic valves. As previously stated, this increase in strain can lead to many heart-related complications, such as calcification, heart attack, atherosclerosis, heart arrhythmia, and heart failure. Some ways we can better our approach a second time around would be to make less assumptions, model the system using a computer program, and to more accurately portray the movement of these heart valve leaflets. Thanks.